like to tell you about my kids, not just because I'm a proud dad, but also because I think their early experiences provide an interesting perspective on the different ways that we've thought about creating intelligent systems. So Max, when he was a baby, we decided at one point that he was old enough to graduate from his crib to a big boy bed. So we swapped out the crib, we put the bed in, we put him to sleep in the crib, and the next morning, he called to us to ask us to, take him out of the bed so that he could start his day. And so we went in and we explained to him, okay, look, this is how a bed works. You're only this many inches off the floor, just sit down on the bed, put your feet on the floor, you're good to go. So we never had to tell him again, but it wasn't something that he came up with on his own. And this was kind of a typical property of Max, that he would follow rules, in some cases very complex rules, but he tended not to discover the rules on his own. Now contrast this with Molly. Now, when Molly was a baby, at one point, we just found her wandering in the morning around the entire apartment. She had gotten somehow her tiny little body over the barrier of the crib, into the room, got out the door somehow, and was just going about her business. At which point we decided, okay, well, I guess she's ready for a big girl bed. And that was kind of a property of Molly pretty frequently. What she would tend to do is create her own rules. She would look at the environment, understand the patterns that were going around, and decided for herself what to do. And this was great. This was very powerful. There was less that we had to tell her about what to do. On the other hand, it made her somewhat uninstructable. So if we wanted her to do something, it was difficult to tell her what to do because she kind of already had her own idea of what needed to be done. And so these same descriptions actually apply to the two main ways of making AI systems. So GoFi systems, or good old-fashioned AI, is when we build intelligent systems by programmers, people, writing down lots of rules, giving them to the system, and then having the system do inference and problem solving to actually use those rules to decide what to do. In contrast, machine learning is a method for creating intelligent systems where what we do is we create a program and then we dump tons and tons and tons of data on it, at which point it extracts patterns, it finds regularities in that data, and then it applies what it learned to solve the problem that it was originally set out to solve. And these are both very powerful and very, very useful ways of solving problems. But I want to argue that there's still something missing. There's still something about these that doesn't really get us all the way there. And to try to get this idea across, let me give you a scenario. So let's say that what you'd really like in your life is to have a robot that will bring you coffee in the morning. Now, I use this example in particular because I've watched a lot of movies, and I'm pretty sure that what Hollywood wants us to do is to make robots that bring us coffee in the morning. Anytime there's a movie with an inventor in it, if it's Back to the Future or Pee-wee's Big Adventure, there's always an inventor in it, and the inventor always is inventing ways of getting us our coffee in the morning. So I assume that that's what we're here for as AI system creators, and I accept that responsibility. So let's say that that's what we want to do. We want to get you your coffee in the morning. So you decide, okay, this is what I need to do. I'm going to create such a robotic system. The first thing you realize is that you're going to need some kind of physical robot. So you go down to your local home robot store, and from all the different robots that are available, you decide to pick one out. Let's say, that's a very nice robot. I will name him Jeff, and I will bring him to my house. So you go home with Jeff, and now Jeff is ready to help you. But Jeff doesn't know what you want. And so you now have to create some kind of program, some kind of AI system that's going to drive Jeff to solve the problem that you want to solve, which is getting you your coffee. So you being, say, a GoFi person, you're like, I'm going to create a good old-fashioned AI system. I'm going to write a program that the robot will follow, and by following that program, will solve my problem. And what you discover very early on, even though you're a great programmer, programming robots is actually really different from programming other kinds of systems. It's very complicated. You have to handle lots of weird corner cases. The programs themselves become very, very complex, very difficult to maintain. So maybe you get frustrated, and you're like, you know what? No more with the GoFi. I'm going to switch over to machine learning. I heard that's very good. You discover right away that this actually does seem to be a lot better. Instead of having to tell the robot what to do in every given possible situation, you have to define an objective function. You have to define what the rules are that it should try to follow. And the rules are, I should have coffee at some point in the morning. You shouldn't break any mugs on the way to do that. And don't make too much noise when you're making coffee, because that wakes me up. And you can define that as a series of kind of costs. And then you say to the robot, great, these are your instructions. Now make it so. And what you discover is that even though it started off as a pretty easy thing from your perspective, it's still pretty frustrating because the robot doesn't figure it all out instantaneously, it has to learn. And what you find is, at some point, the robot, weeks later after you've been waiting for your coffee, the robot has discovered that it's wandering the house, it maybe doesn't know about coffee mugs, but it's got a potted plant, and it's not really bringing coffee to you in your bedroom, it's kind of hanging out in the bathroom for some reason with a cat, and it's not even your cat. Like, what is going on with this? You're patient until you wait, and a few more weeks later, the robot is getting, we'll say, better. It's got a coffee mug now, and it's in the kitchen, so that seems relevant. It's still got that cat, though. So you become frustrated. And probably what you would do, probably what I would do in that situation, is try to intervene in some way. It's like, yeah, it would be great if it could just spontaneously invent all the things that I needed to invent, but it would save a lot of time if I could just tell it what I wanted it to do. And so that's the essence of the idea that I want to put forward, a notion of cooperative artificial intelligence. Cooperative AI is supposed to have in it the strengths of the two other ways of creating artificial intelligence systems. Like machine learning, it's embodied in the world. The robot is in the world experiencing things, and it can ground its experiences in the task that it's actually trying to carry out. But like GoFi, we as the programmers, or we as the people in the system, get to actually define the task that we want it to carry out. So we get to help the system do what it should do to help us. So the basic idea here is that the human trainer, the person, actually becomes a really central component in the creating of the AI system. And what the person's doing is providing feedback on desirable behavior. The person is guiding the learner's attention, so all the zillions of things it might pay attention to, it pays attention to the stuff that matters. And then finally, the human trainer has the opportunity to give the robot certain kinds of experiences in a certain kind of order that help it build up the conceptual structure that it's going to need to solve the problem. And that part, I think, is really neat and very much underappreciated in the field. So let me focus in on that idea a little bit. So when we're training a robot in this model, we are presenting it with a series of tasks, and those tasks need to be selected in a certain way. The learning challenges should be introduced so that they're neither too big of a step, and therefore maybe too difficult to solve for the system, nor too small of a step, that is to say, not making enough progress towards ultimately what you're trying to teach. The tasks themselves need to be relevant and unambiguous and useful, so the robot should be paying attention to what you're telling it. And ultimately, if these things work, the competence of the robotic system comes from climbing up this ladder of competence. By solving each of the individual tasks that you set for the robot, it's going to get better at what it is that it's supposed to do. Now, I call this the portal theory of intelligence. It maybe has gone by some other names. Oh, okay, so Jeff is pointing out that, in fact, the psychologists and education theorists know this as the zone of proximal development, the idea that you're always teaching a little bit outside the current competence of the learner. Now, I didn't know that term when I first started working on this. I didn't spend a lot of time reading the educational literature, which I probably should have. In fact, I was spending a lot of time playing video games, which maybe I shouldn't have. Portal, if you don't know about it, is a video game that's really cool, and I'm going to tell you a little bit about it because I think it's actually useful in this particular context. So Portal is a first-person shooter, but you don't shoot bullets, you're not killing things, you're actually shooting doorways at surfaces. When those doorways exist, it actually connects points in space and lets you pass through them, hence the name Portal. It's a little bit hard to see in the first-person viewpoint, so let me just show you one of the challenges in a schematic way. So here you are in the world, trying to get out of the world, trying to get to the big red button, which is going to let you out. And what you notice very quickly is that the shelf, the barrier before the button, is a little bit too hard to climb up, a little bit too high. But what you've learned over a course of a series of levels is that you have this portal gun, and you can use it to shoot doorways at things. And in fact, if you shoot a doorway where you're standing and one close to the button, those two places in space become connected. And then all you have to do is walk through one of them, and you appear out the other one, and you get to where you're going. So this is actually a really nice trick. It would be very fun if we could do this in the real world. But in this artificial world, you can totally do that, and you need this to be able to solve the problems that are posed. And this isn't the only way to use a portal. There's other ways to use Portal. So let me give you another example. So let's take the same scenario, except now the wall next to the button is gone. So you can't shoot a portal there. You can't come out next to the button. What are you going to do? So what happens is the designers of the game have created a series of levels that introduce all the ideas that you're going to need and just leave you right on the edge of putting those ideas together to solve the problem. And what you realize when you think about this for a while is, wait a second, if I put a portal on the floor and one on the wall high above me, and then jump off the shelf into the hole, I will fly out of the other hole with the same momentum that I went into the hole with, jumping over the ledge and landing on the button, ta-da. All right, so this is a really neat trick. And again, it doesn't happen this way in the real world, but in this artificial world, you get to learn how to use these particular kinds of tools. And the game designers teach this to you and create this competence in you by introducing you to this series of levels. It's really a very beautiful idea, and it's very similar to things that you might think about doing in the real world as well. So, for example, let's imagine that you have a dog. If you want that dog to clean up its own toys, if you go online and search for that as a task, you'll find instructions for the things that you need to teach the dog, the portal levels that you need to expose the dog to get it to solve this task. It's not a matter of just holding a treat and saying, clean up your toys, right? You have to kind of get the dog to that point. Same thing happens with, say, teaching a kid to swim. You don't want to just take a kid and throw the kid into the ocean. This is how my dad taught my cousin to swim, and it's not recommended. Really what you want to do is work up to it in a series of challenges. And so again, I went online, and these are the instructions for learning to swim. If you want to learn advanced mathematics, again, you want to start and build up from there. And it's not just for kids or animals either. If you want to become a CEO, you can go online, and in WikiHow, it tells you just how to do it. There's a series of levels to it, like portal levels, and each one is, relatively easy given the ones below it. And the end, CEO. Now, I haven't tried this one out, but I'm tempted to at some point. So let's take this idea and bring it back to the problem of bringing coffee, because those other problems were not really as important. So the coffee problem, to solve the problem of the robot bringing coffee, one thing that it's going to need to be able to do is recognize your coffee machine, your coffee maker. And so this can be set up as a supervised learning problem. So supervised learning is the machine learning problem of being able to recognize patterns and classify things as being positive or negative instances of a given concept. So if I want to train my robot by supervised learning, what I need is a giant database of images, most of which I label as not the coffee machine, and some of which I label as a coffee machine, and then it would have to go through that data and work out a concept that would correctly separate coffee machines from non-coffee machines. And this actually is a problem that's fairly well solved today. So convolutional neural nets are a very powerful computational tool that if you dump tons of data on them like this, they will probably learn to recognize coffee machines. And if you crack open the container and look inside to see what they're doing, they basically discover portal levels. So the way that these systems actually recognize complex objects is by recognizing straight lines, and using that to recognize curved lines, to recognize textures, to recognize object parts, and ultimately to recognize the objects that you're interested in, which is really kind of amazing and very powerful. Now, you might be tempted at this point to think, okay, well, this is great. This is a solved problem. Anything that I want, I can just get enough data and apply it. It turns out, though, that we've known since the 90s that it's a computationally intractable problem to train neural nets or machine learners in general, in the worst case. I mean, lots of problems they solve really well, but others, they're going to struggle on. It turns out the problem, if you could solve it effectively, you could use that same system to break cryptographic codes, like the kinds of things that protect our money in the banks. So we're expecting, at least the bankers, I guess, are expecting that this is a hard problem and unlikely to be one that we could solve. But what my students and I have figured out is that, in fact, if you as a teacher can break down the learning problem into portal levels, if you will, you can actually train any task, no matter how complicated, it's in such a way that the learner is never having to work too hard. Each of the levels that it solves are simple combinations of the things that it's already seen. This works for supervised learning. It turns out it also works for reinforcement learning, which is the problem of actually following a path to get to a goal, to execute a sequence of commands in the world to, in this particular case, go from the charger to the kitchen to my bedroom to deliver coffee. This problem is also intractable for a completely autonomous system. We just give it the task and just say, go for it. It's going to take essentially forever. But we can break it down into smaller problems, and we can solve it that way. It's not easy to know how to break it down, but there is a community of scientists who think about this, the behavior analysts. These are the people who think about how to train animals. How do you train a chicken? How do you train a dog? How do you train a hippopotamus? And what they do is they teach people how to break complicated tasks into smaller pieces. And one of the challenge problems that they'll give is, okay, train a chicken to walk a figure eight. And it turns out it's actually not that hard if you break the problem down the right way. My colleagues and I were reading about this and thought, this is really amazing. We should totally do this with a robot. So we built a robot that you could give positive and negative feedback to, like a chicken, and we gave it things to walk around in a figure eight and trained it just the way that the behavior analyst would tell us to. And it worked. We got a robot that could then run around and do a figure eight. It was really neat. It was almost as if robots were following in the chicken's footsteps. So this notion of cooperative AI, to me, it's a very powerful idea that is really our best hope to creating intelligent systems. And I think one of the reasons I'm so optimistic about this as a path forward is because it acknowledges an important fact about intelligence that I think is underappreciated, and that is the intelligent system that we know the most about, namely people. We don't solve super-duper hard problems always on our own. If we need to use something complex like language, we invent language together. If we need to use advanced mathematics like calculus, we learn this together. Even the inventors of calculus didn't invent this completely alone, right? So both Newton and Leibniz created calculus at around the same time and around the same way, but they were both building on the notations that were available at the time, the problems that people thought were interesting, the concepts that were available, and they came up with something very similar to each other. In fact, Newton even said, if I can see so much further than others, it's because I'm standing on the shoulders of giants, right? I'm getting benefit from working with other people. So we really do get to be smarter by working together in this way. But smartness is not the only thing we care about. When we're building AI systems, we really want them to be helpful. We want them to do what we need them to do. And this cooperative approach to artificial intelligence is maybe problematic in that regard. It really puts the onus back on us as teachers to teach the systems the right things. We don't want all of our robots to grow up to be, I don't know, racist Twitter bots, because this happens sometimes. And so you want to avoid that. So we really have to pay attention to what we're asking our robots to do. We need to teach them well. But I think the benefits of doing so are really important. Well, in the near term, we'll have systems that are more personalized to the problems that we're actually facing. In the longer term, we'll be sharing the world with intelligent agents that kind of get us. They understand the things that we understand. They break down the world the way that we break down the world. We'll understand what they're doing. They'll understand what we're doing. And I think that's really important because in the coming AI revolution, each of us has an important role to play. We're not going to be sitting on the sidelines. We're going to be putting a bit of ourselves into these systems that are so powerfully going to influence our lives and our futures. Thanks very much.